Welcome. This episode is about networks and graphs, data structures, and the way in which we can visualize them. So we'll start off just by looking at a simple network structure, which is a tree, a special case of a graph or a network. And in trees there's a single root node, and each child from there going down the tree has a single parent going up the tree. So you can have a branching structure with a number of branches at each parent node. In this case, the example here is a binary tree because each parent node is divided between two child nodes. But there's always this structure of one parent to a number of children. Nodes in the tree or in the graph structure are atomic entities that might store data, any number of attributes that you wish. And edges connect two nodes and may also store attributes related to that connection. So there's lots of possibility in a tree or graph for storing data and attributes about the nodes and edges. The main difference between a tree or a graph is that within a graph you can have cycles, and that means a number of nodes can be connected by more than one path through the network. If you choose any two nodes, there might be two or more different ways of getting there. If you're looking for references, just to remind you of the background for these things, there's a free online resource, Data Structures and Algorithms by John Bellinaria, or if you like books, there's a Data Structures and Algorithms in Python book by Goodrich, Tomasiu and Goldwasser, which is an excellent text for all sorts of algorithms in computer science and very clear examples of how to implement and use them. If we look at how you store a graph or a network, then there's two parts to this: how you store the nodes and how you store the edges. This example here, the nodes are stored by their label, A, B, C and D. You might also have a numeric label for nodes. And in this case, each node also has a number of attributes. It has an X and Y position, which plot where it is on the page, and also a data value, and in this case it's called outMean. It's an abstract value here, and in this example we've used the XY value to locate the node, to plot it on the page, and we use the mean value to colour it. So things with a similar mean value are going to get similar colours, like A and C. And things with very different mean values, like B and D, are coloured in this case on a very different colour scale. Alongside the nodes you also need some form of edge structure, and the edge table here records between each node a source and a target pair. So wherever there's an edge, there's a source and a target pair here. In this particular example, it's undirected. We've not said that there's a particular direction in the graph visualization, but it's somewhat implied in the edge table as having a source and target. So those key features are summarized here. You need a location with each node to give you the layout. You need an attribute value for the nodes, which outMean. And in this case, the edges have no attributes, and although there's an implied direction, we've not drawn a direction on the plot. If you want to have directed edges, in this case this is visualized with Mathematica, you can tell it to draw the edges as directed, and it will then take the source node as the start and the target node as the end, and you'll see that arrows have been added onto the plot here. Sometimes this is meaningful, sometimes it's not meaningful. So sometimes it is important to know the directions on the edges, sometimes there is no semantic relevance in the application. So here's an example of a more complex graph structure. This is the London tube map. I think this is almost all the stations and lines in the map. And you can see how quickly something becomes too complicated to view. So the centre of London there, it's impossible to read the stations. You can just about do it on some of the outlying stations on the furthest apart lines. Again, this is visualised in Mathematica, and we'll come back to using the tube data later with Python. If you want to, you can download this data from these two links. So here's a simplified version of that. So we've taken that and we've just taken all of the stations, all of the nodes that are in zone 1 of the tube fare structure in London. You'll notice that between High Street Kensington and Bayswater there's no link. That's an oddity in the data, and we'll come back to that later. But that's all the lines within central London, and visualised with undirected edges, and you'll see how it's used arcs to visualize multiple connections. When multiple lines run between the same two stations, multiple types of train, then you'll get that double or triple or quadruple connection between nodes. We haven't labelled the lines differently or coloured them differently here, they've all been drawn in the same way really. And we can simplify this one level further. We can just pull out the circle line. So these are all the stations in the circle line and the edges connecting them. And this is plotted geographically. So each station is at its geographical latitude and longitude position. Topologically, it's no different to a circle, even though in practice the trains look like they're going to have to go around some quite sharp corners to get between stations. And finally, one last thing on networks. This is Harry Beck's 1936 design of the map of the London Underground to try and simplify it and clarify it. So here it doesn't retain distance or angles of the lines, it doesn't retain position, so it's not really very good for judging how far apart stations are in the real world, but it was designed to allow you to plan a route between two stations quite quickly and easily by only allowing lines to run horizontally or vertically or at 45-degree angles. And there you see the result, and it gives a clearer layout, I think, in many ways. Okay, so that's a quick introduction to graphs. So for now, thank you for watching. Back soon.